Hi everyone, this is the beginning of chapter 10. It's titled Acid-Base Titrations. There's going to be 3 parts and this is part 1. Let's get started. So as we know, in a titration we measure the quantity of a known reagent required to react with an unknown sample. From that quantity, we can actually deduce the concentration of an analyte in an unknown. We're going to start with the easiest kind, which is acid-base titrations for strong acid with a strong base. The goal of all of these problems is to be able to make a graph showing how the pH changes as you add titrant. If you can do that, then you understand what's going on in this process. So the first thing you need to do is write a reaction between the titrant and the analyte. That makes you think about who is in the burette and who is in the Erlenmeyer flask. So let's consider a titration of 50 mils of 0.02000 molar potassium hydroxide with 0.1000 molar hydrobromic acid. The reaction, since it's a strong base and a strong acid, you know it's going to be just pure water. That's the only thing that's reacting here is H plus and OH is going into water. And if you were to take the equilibrium of that reaction, you would see that it's a value of 10 to the 14th. Because remember, in the equilibrium expression, we don't include pure water, so that's why there's a 1 right here. And H plus OH is Kw. So 1 over 10 to the negative 14th is equal to 10 to the 14th. Since that equilibrium constant value is so large, we're pretty safe in saying that it goes to completion. And this goes for every reaction that you have with a strong acid and a strong base. It's going to go to completion. So let's decide who is the titrant and who is the analyte. Well, since they tell you that they're doing 50 mils of 0.02000 molar KOH, that's the guy who's going to be in the Erlenmeyer flask. So what you're adding is the HBr. Prior to the equivalence point, any acid or H plus that you add is going to be eaten up immediately by the OH in the flask. A useful starting point for the strong base, strong acid titrations is calculating the equivalence point. If we have 50 mils of a 0.02 KOH with 0.1 HBr, to find the equivalence point, it's very easy. All we got to do is take the HBr molarity, which is 0.1, multiply that times VE, that's going to be your equivalence volume that you're trying to find, is equal to the molarity of the OH and the initial volume of the OH. If you solve all of that, you'll see that your equivalence point is 10 mils. When you add 10 mils of HBr, that titration is complete, which means that all of the OH that was in the flask has eaten up as much HBr or as much H plus as it can. So prior to the equivalence point, excess unreacted OH is present. After the equivalence point, now there's no more OH left. There's excess H plus in the solution. There's 3 regions. Before the equivalence point, the pH is determined by the excess OH in the solution. At the equivalence point, the added H plus is sufficiently enough to react with all of the OH in that Erlenmeyer flask. And the pH is determined by the dissociation of water. You know already that since it's equal to each other, H plus is equal to OH, that pH is going to be 7. And that is so cool because you already know the pH of a strong base, strong acid titration, always. It's not the same when you do other types of titrations, but for this one, the pH is going to be 7. Now, after the equivalence point, the pH is now determined by the excess H plus because all of the OH has been eaten up in that flask. So now you've got extra H plus in there. So let's do an example to calculate all 3 regions. Region 1, before the equivalence point. Remember, this is the region that's dominated by the excess OH. You've got more OH than you have H plus. Before you add any titrant or any acid, what does the flask actually contain? Well, we have 50 mils or 0.05 liters. And what is the molarity of that? Well, they told us it was 0.02 KOH. So multiply the volume times the molarity, it'll give you the number of moles of OH. So if you do that, you get 0.001 moles of OH. Now let's say we add 3 mils of HBr. How many moles is that? Well, we're going to take 0.003 liters times the molarity of the HBr, which is 0.1, multiply those together, that gives you how many moles of H plus you're adding, which is 0.003 moles of H plus. How much OH actually remains? Well, you started with 0.001, you added 0.0003 moles of acid, so how many OH moles are left? It's 0.001 minus 0.003. It's equal to 0.0007 moles of OH. Now, what is the total volume in the flask? Remember, you added 3 mils, so obviously it's not 50 anymore, it's going to be 53 mils. If I was to ask you, okay, give me the concentration of OH now after you've added those 3 mils. Okay, so you take the moles that you have of OH after you added the 3 mils, which is 0.0007, we calculated that, divided by the amount of total volume, which is now 53 mils. So 0.053 liters, you have your molarity of OH. And now you can answer what's the pH of that analyte in the Erlenmeyer flask. Well, POH is negative log of OH. You've calculated what the concentration of OH is. So if you take 0.0132, you take the negative log of that, you should get 1.879. Remember, this is POH, so you would take 14 minus 1.879, and that gives you a pH of 12.12. If you wanted to figure out what the pH was before you even added any titrant, all you would have to have done is take your concentration of OH at the beginning, which of course they gave it to you, right? It's 0.02, and take the negative log of that. If you do 0.02 and take the negative log, you'll get 1.6989. Remembering that that's OH, so you would have to take 14 minus 1.6989, you'll get 12.30. So that's the pH that you started at. You added 3 mils of an acid, of a strong acid, and now your pH is 12.12. So you see, this is how you start creating the graph, this graph that you'll see the titration curve, which I'm going to show you at the end of this video. What about region 2? Well, that's the easy part. This is the part where enough H plus has been added to eat up all the OH in the Erlenmeyer flask. So we know that this is the dissociation of water. The equilibrium constant is going to be x squared. Just x right here, as we've done the equilibrium constants before. And we know that Kw is equal to 1 times 10 to the negative 14th, which means that each x is equal to 1.0 times 10 to the negative 7th. Remember, we just took the square root of that. And that would end up being a pH of 7. So the pH at the equivalence point in a titration of any strong base or acid with strong acid or base, whichever one you're doing, will be 7 at 25 degrees Celsius. Obviously, it's not going to be 7 if you're at a different temperature, but at 25 degrees C, it will be 7. So this is the easy part. What about region 3? Well, region 3 is dominated by excess acid, because you've already eaten up all of the OH in the Erlenmeyer flask. So let's try to figure out at 10.50 mils, right? Remember that the equivalence point that we calculated was 10 mils. So if we add 10.50 mils of acid, we've already gone over the equivalence point. So let's see what the pH is then. At 10.5 mils of acid, we have added 0.5 mils extra of acid. So let's find out how many moles of acid we have extra. So it would be the milliliters of acid that we've added, which is in liters would be 0.00050 liters, times the molarity of the acid, that doesn't change, which will give me how many extra moles of acid I've added after the equivalence point. What is the pH? Remember, the original volume of the solution was 50 mils. We've added 10.5 mils of acid total, which gives us a total of 60.5 mils. Now to find the concentration of H plus, since we're after the equivalence point, the concentration of H plus is dominated by how much extra H plus has been added. So it's what you calculated. So your concentration of H plus would be 0.00005 moles. And excuse me, I only have 3 zeros there, but I made a mistake, so just add one more zero. It would be exactly what we calculated up here. 0.00005 moles divided by the total volume of the solution, which is 60.5 mils or 0.06050 liters. That gives you a total concentration of H plus of 8.26 times 10 to the negative 4 molar, which of course you can convert into pH, giving you a 3.08. So the whole point, like I said before, is to create this curve. And right here, I'm showing you the calculated titration curve that shows how the pH changes as you're adding acid. So if you see here at 0 mils of acid added, look at the beginning pH. It's at 12.3. And we could have calculated that. And then as you add a little bit more of acid, a little bit more of acid, a little bit more of acid, you'll see that that pH curve starts going down until you get to your equivalence point. At the equivalence point, you're going to have this straight line because it's going to shoot up from a, if you're starting with a base, it's going to shoot up from a basic pH really, really low to an acidic pH, because that equivalence point is the most drastic. It's the steepest point. And you notice that the equivalence point is exactly 7 because you have a strong acid and a strong base titration. In your book, they have this table, which is 10.1, which shows you that all the points that they use for their curve. And if you notice, we calculated several of them. We calculated the milliliters at 0 degrees of acid added, which you can see here is 12.30 pH. We calculated also at 3 mils, which obviously you saw was the pH was 12.12. We calculated the one exactly at 10 mils, which that's at the equivalence point at 7. And then we actually calculated the last one, which is at 10.5, and it gave us a pH of 3.08. But I would urge you to make sure that you understand every single one of these and you're able to make a titration curve. Because again, if you make the titration curve, then you understand what's going on. Let's try to do a problem to see if we understand what's going on. It says find the pH when 12.74 milliliters of 0.08742 molar sodium hydroxide have been added to 25 mils of a 0.06666 molar perchloric acid. First step is to determine who's the titrant, who's the analyte. So if you do that, you should get that the analyte is the acid. I mean, it tells you right there, have been added to 25 mils of 0.066 perchloric acid. So the titrant is, of course, the base. The second step, find what the equivalence point is. That way you would know, okay, so is the number they give me before or after the equivalence point? So the equivalence point would be 25 mils times the molarity of the acid. That should give you 0.0016665 moles. And then you divide it by the molarity of your base. You do that, that gives you 19.06 milliliters. So at 19.06 milliliters of base that you add, that's the equivalence point. Now, they want you to find the pH at 12.74 mils of base added. This is obviously before the equivalence point. So who is this region dominated by? It's going to be dominated by acid. So now to find what the pH is, then you would first figure out, okay, well, how many moles of H plus did I start with? I started with 0.0016665. How much base have I added? You would take 12.74 times the molarity of the base. That should give you 0.0011373. You subtract what you have from what you started with, and that'll give you 0.0005527 moles of acid. That's how much acid you have left after you've added that 12.74 mils of strong base. To find the pH, you would take the concentration of H plus. So that would be the moles of H plus that you have left, which is that same number, 0.0005527, divided by the total volume of the solution now. So it would be 37.74 mils. That'll give you 0.014646. That is your H plus concentration. So to find the pH of that, just take the negative log of that number, and you will get 1.83. So this is all that I have for this video. We're going to continue on with part 2, which talks about the titration of a weak acid with a strong base. All right, guys, see you later.